Hi everybody, welcome to part 2 of our PCA and regression walkthrough. There's a part 1 to this video, so if you haven't watched that video yet, kindly watch that first before watching this. Okay, let's go straight ahead to our material for today. In the last video, we performed PCA, principal components analysis, and found an underlying structure out of data coming from 4 variables that produced a 4x4 correlation matrix that defined a 4-axis system with 4 principal components where all the axes or components are perpendicular or orthogonal to each other, and found 4 scalars or constants that distributed the explained variance or co-movement of the correlations across those 4 principal components. These are the eigenvectors and eigenvalues, respectively. As a result, we use variable 1 to proxy for the floor size factor and drop variable 2. We dropped variable 3 and grouped the data by clusters instead. And we use variable 4 to represent the explicit factor lot size. Here we reduce dimensionality by just using 2 variables out of 4 variables, using our PCA, retaining 94% of the explained variation even when we drop 2 variables from any future regression. And in this video, we'll do the multiple regression and finish the analysis. Now, this is what the data looks like. We've added the price column. So now we're in a position to complete the multiple regression using this. And as usual, please check the video information below to download the data. Now, we're going to do 2 things here. We're going to do a lazy regression and just use all the independent variables together in one go, simulating what would happen if we just went straight ahead and did regression without doing any prior preparatory work on the data. And on the other hand, we will do a smart regression where we will use the PCA and the analysis we did in the previous video as some sort of prep work. The result of the 2 ways will be compared, and we will also present the idea of the root mean square error to settle which one is a better model. Now here are the results of the lazy regression, and we present the formulas below to translate the tabular results in equation form. So the coefficients are 46726, 67940, and so on and so forth for each of the variables, and then they're represented below with the equation. One in the usual y and x format, and then in the more explicit price equals the coefficient times variable plus a constant. We note that the constant is actually not significantly different from 0 using a 0.10 alpha. So we'll drop that coefficient, and from here on, we'll just use 0 every time a coefficient is not significantly different from 0. And this is what it looks like. Here's a table with a forecast called the estimate column here in the table. From here on, we're going to get the error, meaning the actual price minus the estimate. That'll be the error. Then we square that error, and then eventually summing up all the square errors seen here below. But why do we square the errors? This is because what we actually want are analogs of the variance and the standard deviation. We want to get the average square errors, which is essentially some sort of variance number, and then get the square root of the average square error, which is some sort of standard deviation number. And so in modeling jargon, the square root of the average square error is called the root mean square error, or RMSE, and it's analogous to the standard deviation. And when choosing models, we will prefer the ones with the smaller RMSEs. For the lazy model, the sum of the square errors is this one, 83,666,654,529. So dividing that by 20 to get the average, we get 4,018,332,276. And this is the average square error. Next, we get the square root of the average square error to find the root mean square error, and here it is 63,390. Moving on to the smart regression, we are left only with the bedrooms and lot sizes as the variables. And we will do the regression by clusters, city addresses and provincial addresses. We will also use the color scheme to distinguish the data, blue to refer to city addresses and green to refer to provincial addresses. These are the regression results for the 2 clusters. It turns out that for city addresses, only lot size is significant. For your provincial addresses, all coefficients are significant, so we will use all inputs. Again, we shall look at the sum of the square errors here for both clusters. Then we're just going to sum it all up to get one value for the complete data. Then get the RMSE. Here, the root mean square error is 23,339. Taking a look at the side-by-side comparison of the lazy regression versus smart regression, we see that the RMSE of the smart regression is smaller, so this will be the preferred model as it indicates a lower error number. Alternatively, we can get the RMSE per cluster, and still the smart regression shows lower RMSEs, so it would be really the preferred model for predicting prices. What are our takeaways for this one? The smart regression beats the lazy regression from an analysis of the resulting RMSEs, implying improvements in modeling with the use of PCA before doing the regression. Now, all discussions about eigenvalues and eigenvectors, they have no more bearing on the regression as it's really more for preparatory work and the analysis so that it will inform the overall regression process. From an analysis point of view also, the lazy regression does not provide useful intuition behind the model, unlike with the smart regression. For example, here's the lazy regression model. While it appears that having more bedrooms is beneficial as it adds 67,940 per bedroom to the price, it's strange to see that having additional bathrooms reduces the value by 91,200 per bathroom. This is a usual problem when two variables are highly correlated and are included in a regression. They will tend to look like they are offsetting each other without rhyme or reason, making it hard to intuitively reason out a model result. It's also a bit baffling to see a deduction of 158,000 plus for provincial addresses or address equals 1. Perhaps this can be an indication of cheaper provincial prices for real estate, but a flat amount looks a bit too rigid. Analyzing the smart regression model for city addresses, for example, in this model, only lot size is important to determine the prices in the city. This might be meaningful in the sense that bedrooms are immaterial since the lot size already prices in whatever number of rooms can be accommodated, meaning you don't artificially increase the prices by just adding more bedrooms in the city model. Again, just a reminder, this is hypothetical. And for the provincial address in this model, both number of bedrooms and lot sizes are important. And there's also a constant. However, there's still something problematic here. How to explain the negative constant starting price of 68,415? Perhaps similar to the city model, it can be explained away as a balancing account to offset what might be priced in by the other variables. And again, just a reminder, the data is hypothetical, and the analysis done here is meant to simulate a walkthrough from PCA to regression to see the kind of analysis that can happen in real life. That is the point of this video. Things can get even messier and less straightforward in real life. And this indicates that this is as much art as it is science. So kindly keep that in mind. And finally, as a summary, for multivariate data, it's useful to first do some principal components analysis to reduce dimensionality and have fewer variables to work with, especially if you have a large number of variables, before doing a multiple regression. For one, it can help address multicollinearity issues, or it can simplify the regression and provide more intuitive results, or it can provide a framework for understanding the variables like the factors that drive the model. In the end, though, it's still the multiple regression which provides the predictive modeling. And with that, we end our walkthrough from PCA to regression. We hope that you find this useful and that you can use the Quantprof Lite add-in for your analysis. We'll be having one more exercise on PCA next time. So meantime, see if you can reproduce the results here by using the Quantprof add-in and the dummy data provided. It takes time to internalize the ideas presented here. So actually redoing the exercises yourself should be very useful to acquire the analytical skills required here. And that's all we have for now. Please like and subscribe to help support the channel, and see you next time.